Okay, for this problem, we need to determine if we need a free body diagram or not. If you look at what they're asking for, they're looking for a length, which is a position of something. There's no part B. Okay, so it's not a dead giveaway. They're not asking for a force. So you have to count the degree of freedom. So you ask yourself, what's the degree of freedom? Well, can something move? Yeah, that yellow block can move. It can slide on the blue surface. And so that's one motion. So if you prevent it from sliding, can anything move and not fall apart? And the answer is no, because what they're saying is that this block does not lift from the cylinder. If it doesn't lift from the cylinder, then you stop it and nothing can move. Okay, so it's 1 degree of freedom. What that means then is if you tell me one acceleration, I can find all accelerations or position, for example. So the unstretched length, that's basically a position. So so the question is, do you tell me an acceleration or a velocity or something like that? The answer is no, you don't. At this 60 degrees, when the angle is 60 degrees, you have no idea what it's doing. You know it starts at rest, but that's all you know is, it doesn't stay at rest. You have no idea what it's doing. So the answer is, yeah, you need a free body diagram. Now, you could do a free body diagram of the blue surface, but you would have to worry about all these forces down here that are holding it down. You don't really care what they are, and they're complicated. Let's not do that. The spring has got, you might want to draw a free body of the spring, but there's no mass in there. So I'm thinking, I don't really want to try that. So the only thing left is the yellow box. So I'm going to do the free body diagram of the yellow box. Okay, so normally you should separate the free body from the rest of the system, but I'm drawing it over here so that you can kind of get your bearings as to what everything is doing. Now the forces are in blue. So you have gravity, right? So you have this gravity force, and it always points down towards the center of the earth. So that's why it goes straight down. It has nothing to do with the blue surface. The contact has nothing to do with that. It's straight down towards the earth. So that's why it points straight down. This other blue force right here is the spring force. Spring forces are equal to the spring constant, which is given right here. It's equal to the spring constant times the amount that it's stretched. The spring force always points along you draw a line between the two ends of the spring, and the force has to be along that line. So it either pulls down, if you stretch the spring, it pulls down, or if you compress the spring, squash it, it will push back out. So in this case, the blue arrow points along the spring, and because it's holding it onto the surface, I think it's pulling it down. I'm going to calculate that, and I'm going to find out if in fact it does. Okay, so I assume it goes inward. So that's why the direction is there. It always points along the spring. The other force is a normal force, and so that's shown here. The normal force is always perpendicular to the contact. So this is going to be perpendicular to the blue surface. That's the contact surface. So the normal force is always that way. This is a pressure between the two surfaces, so they push away from each other. So the blue body pushes the yellow body in the direction that's perpendicular to the blue, right? In this case, I'm saying it's equal to 0, and the reason it's 0 is because when it gets over there at 60 degrees, it's lifting up. That's what they say. And if it's lifting up, it's breaking that contact. So the normal force, I know, is going to be 0 in this case. So the free body diagram consists of these 3 blue forces. Now, what do you do after you draw the free body? You sum forces. So in this case, in what direction? Well, you need to think about it. You want to do horizontal and vertical, whatever makes acceleration easy. I don't think that's smart, because I don't think I have an easy expression for the acceleration horizontally or vertically, because it's on a curve. So the next thing I'm going to think about is, well, do I want to use tangent normal or do I want to use r and theta? In order to do tangent normal, you have to know the path, which you do. It's a circle. You also have to know speeds and changes in speeds. I'm not sure I have that. They talk about angles, so I think maybe this would be an r theta. I'll do it again, and I'll do tangent normal. But anyway, I think it's r theta. Okay, so once you decide what coordinate system, now you draw in your two directions. Now, you have to be careful because they're shown in red. So these red things up here are directions. They are not forces. These are just directions. So you always find the r direction first. It points from the origin straight through the body and keeps going out. So the nr is pointed out. The n theta is 90 degrees from the r. In order to determine whether you go clockwise or counterclockwise, you look at the angle and you ask yourself which way is positive angle. In this case, the way they draw it, if theta gets bigger, this guy is rotating clockwise. So I'm going to go clockwise 90 degrees from the nr, and I'm going to get to the n theta. So that's your nr direction and your n theta. Now that you have the two directions, you just simply sum the forces. So you have a component of mg, so that's given up here, mg cosine 60. It's in the positive, no, excuse me, I'm doing the radial direction. So that would be mg cosine of this angle. It'll get you this component of the force right along here. And it's pointing opposite the nr, so it's a negative. That's why it's negative there. And then the spring force is in the direction of nr in the opposite, right? So that's why it's also negative. K times the stretch, S is the stretch. So those are the forces in the radial direction. That's equal to mass times acceleration in the radial. That's the radial equation for acceleration. Then you sum forces in the theta direction. In the theta direction, you have mg sine theta. That would be the component of mg along this theta direction along here. And it's positive because it's pointing in the positive theta direction. And that's all. So that equals a mass times acceleration. This is the acceleration in the theta direction. All right, let's circle the things that we don't know. You don't know theta double dot. You don't know theta dot. You don't know the stretch. So that's three things that you don't know. Only two equations. You need another equation. How do you know it's not another free body diagram? The reason is because if you count how many unknown motions you have theta double dot, you have theta dot, and you have this position stretch. So that's three unknown motions or non-force variables. And you have 1 degree of freedom, so that means you should only have one of those, but you've got three. So what do you have to do? You have to relate two of them to the other one. Okay, so that's why I realize, okay, I need to relate theta double dot to the theta dot. That's how I know that, because it's 1 degree of freedom. There should only be one of these guys, either this one or this one, but not both. Okay, so I'm looking for a relationship between theta double dot and theta dot. So I've got one. Theta double dot is equal to d theta dot dt. So what I need to do is I'm going to find the theta double dot, and then I just integrate back. That's why I'm doing that and not looking for another free body. Okay, so what I'll do is I'll solve for this guy. R dot is 0, so this term is gone, this term is gone. That's why they're crossed off. So I'm going to solve the bottom equation for theta double dot. Theta double dot is equal to radius, which is 2, right? That's the radius of this guy, 2 times theta double dot. That's the right-hand side. And then over here, I've got the mg sine 60. The masses have canceled, right? Masses have canceled. So this is the bottom equation. All right, so the question is, can you integrate this? The answer is no. Why not? Well, because is this always 60 degrees? No, it isn't. It changes, right? As the thing is sliding over, it changes. So that you can't integrate that. That's not a constant. So you have to be careful when you write these things. Okay, well, what should it be? Well, in general, it'll be the angle theta, whatever theta happens to be. Now you have a formula. Now you can integrate it. Okay, so can you separate the variables? No, right? Why not? Because you have d theta dot dt, that's over here, times 2, but if you notice I'm dividing by the 2. So you have a d theta dot dt, but over here you have theta, not t. So you can't just separate them. Okay, so you got to be fancy. All right, so here we go. I start off with what I know, d theta dot dt, right here. I'm going to multiply by 1, and the reason I choose d theta is because over here it's theta. So I put d theta. Then I switch the bottoms. Okay, then what I do is I say, oh, well, this is d theta dt, that's theta dot. And then the other term right here is this one, d theta dot d theta. All right, and that is these two terms right here are equal to theta double dot. Theta double dot is equal to g over 2 sine theta. Put it in right there. So you have this stuff on the left equals this. Now, can you separate them? Yeah, you put theta dot on the left, all the theta dots on the left, you put all the thetas and d thetas on the right, separated. What do? You integrate. Okay, the left-hand side's easy, 1/2 theta dot squared. Right-hand side's not too hard. You don't forget the c. How do you find the c? The same way you always find the c. You have to tell me a value of theta and a value of theta dot. Okay, well, I know it's at rest when theta equals 0. Put this in there, so you have 1/2 times 0 squared is 0 equals minus 1/2, or yeah, 1/2 g. Cosine of theta, what's the cosine of 0 degrees? 1. So you have minus g over 2 times 1 plus constant. Constant equals g over 2. Take the constant that you have into this red guy, bring him down here. You have 1/2 theta squared. You just add in the c. Just put the c in here. Okay. Now, now that I've done my integration, I'm looking for theta dot because I'm going to shove it into the top equation. So what I do is I say when theta equals 60 degrees, put 60 degrees in for theta, calculate the theta dot, you end up with this. So theta dot, well, theta dot is 4. So theta dot squared is 16.1. So what I'm going to do is I'm going to grab the top blue equation, okay, and I just copied it down. Left out the terms that are gone, so the r double dots is constant, r is constant, so that's gone. So that's the equation that's left. I know what the theta dot squared is, so I just plug it in here, right? mg is 2 cosine of 60. The k is 2 times s. This is mass. Make sure you turn it into slugs, right? Times r is 2, and this is the theta dot squared. So there's nothing left but s. You solve for s. Stretch is equal to 0.5. So the stretch is equal to the current length of the spring minus the free length. If you were to not touch it, cut it loose, and set it down and measure it, that would be the length of the spring. So s 0.5 is equal to 2. That's the current length because it's stretched from here to the edge. So that would be 2 minus the free length. Solve for the free length. Free length is 1.5. Okay, that's it.